Recording again.
So it is a great pleasure to host today Larry Samuelson from the Department of Economics at Yale University. Larry's achievements and activity and service to the community are too long to list. So all I say is that he has numerous fundamental contributions to repeated gains in economic behavior, and that he had collected 59 co-authors so far, and they cover almost all the alphabet. Actually, Larry, you missed only Q and X. So
Javier, something there is no. Oh, that's pity.
Yeah. So now, Larry, the Zoom room is yours, and please tell us about substitutes.
Thank you. Thanks for having me, and thank you all for coming. It's nice to see so many friends and familiar faces. Not quite as nice as if I were seeing you across the table, but still the best we can do. A paper about substitutes amongst, I guess, 2 of the 59, and Lucas probably picks up the V for me. Hold on for a moment. Are Alfred Galachon and Lucas Vernet. A bit of motivation. I have long found substitutes, or the idea of substitutes, quite fascinating. One is we see them everywhere. This page is primarily quotes from intro or intermediate texts that I pick up when I teach, and we explain consumer behavior often in terms of substitutes. We explain competitive markets in terms of there being lots of substitutes, monopoly markets in terms of there being few substitutes, competitive equilibrium. Substitutes gives us nice properties like uniqueness and stability. In some sense, I have this quote here from Gould and Sticchetti: with indivisible goods, the substitutes are necessary as well as sufficient for having existence. In matching markets, substitutes are sufficient and, with the appropriate quotes, essentially necessary for the existence of a stable match. Perhaps one of the nicest illustrations I know of the power of substitutes is, think of multi-unit auctions. And if we have goods that are substitutes in multi-unit auctions, we know there exists nice, simple, efficient ascending bid mechanisms everyone can understand. And in contrast, if we have complements, I go back to the classic chopstick problem of Balash Sventes and Bob Rosenthal, and think about what the equilibrium looks like there. Instead of a nice ascending bid mechanism, each bidder has to identify a tetrahedron in 3 space and then mix uniformly over the surface of that tetrahedron. And so you imagine being hired as a consultant for an auction, and in one room you're trying to explain to them an ascending bid mechanism. In another room you're trying to explain how they're going to mix over the surface of the tetrahedron. And you become a fan of substitutes really quickly in circumstances like that. Substitutes are intuitive. We all understand that these things here are substitutes for one another. And then everyone understands that some things like cans and can openers are not substitutes, that if you don't have the can opener, it really doesn't matter how many cans you have. At the same time that substitutes have this intuitive feeling to them, they can be kind of elusive. When we talk about perfect competition in intro econ, often the market for wheat comes up, and we claim you can't get a more homogeneous commodity than wheat, that there are obviously perfect substitutes for that around. And yet, reading the history of the market for wheat, it took a while to get the notion of substitutes right in that market. It took a while to get the specification of what is meant by different types of wheat in such a place that the categories were narrow enough that the items in them were good substitutes for one another, and yet broad enough that the markets were thick enough that they were really perfectly competitive markets. And so it took some fair trial and error to get an operative notion of substitutes to make that a reasonably competitive market. At the opposite extreme of wheat, if you want two things that are about as far from substitutes as you can get, you think of hot dogs and hot dog buns. These are about as complementary as one can imagine. And yet that gives rise to one of the great puzzles of economics, one of my favorite papers from a long time ago, explaining why it is that these seemingly perfect complements come in different numbers, typically 10 on the one hand and either 8 or 12 on the other. But perhaps the most important things about substitutes is I consider them one of the greatest embarrassments of economic theory, because when you teach introductory economics, you'd like to say something like what it means that two goods are substitutes. And you would expect this to mean that these derivatives are positive, that if the price of one of them goes up, you substitute into the consumption of the other one. You buy more of the other one. And the problem is, we can't be sure that these derivatives will take the same sign. They could go different ways. And so then you can't really say I and J are substitutes. You could try and say things like I is a substitute for J, and you could think that that means something different than J is a substitute for I. But first, no mortal could really remember which one is which when you try to look at these derivatives. And it's kind of embarrassing that we have to make this kind of difference. Now that is to a large extent my motivation for thinking about substitutes. I'm not going to have anything to help us with that today. I'm going to look at a much narrower issue. The immediate cause of this paper, or this work, was a paper by a couple of my colleagues and a co-author, Barry, Gandy, and Hale. And their main result was if we look at a demand function and it satisfies weak gross substitutes, a familiar notion, and in a notion they introduced, connected strict substitutes, then that demand function is invertible and its inverse is point valued. And they thought this was a very nice result to have when thinking about foundations for the empirical work that they were doing. They especially liked the point valuedness of the inverse. And this work started after looking at that paper and Alfred asking me, what would the counterpart of that result be if we had a demand correspondence instead of a demand function? And on the one hand, that's a pretty nerdy question to ask. You start with a property for a function and ask, what's it look like if you go to a correspondence? The sort of question that if a graduate student walked into your office and said, this was what they're going to work on, you might say, maybe think of something else. But we did it anyway. And so we're going to introduce a notion of substitutes for correspondences that we're going to call unified gross substitutes. I'll explain the name as we go along. And so far, that's not a very good fit for a game theory seminar because there's not going to be much game theory in it. But then we're going to introduce two classes of correspondences. I'll spend almost all my time on this one, the equilibrium flow correspondence. And it's going to exhibit unified gross substitutes. That's going to let us do some nice things about it. But it's also going to capture lots of familiar problems as special cases, including things like matching problems. And it's going to allow us to unify some results in these problems. It's going to allow us to extend some results or to lead to some new results. And so it's going to provide us with a tool that we think is going to be useful. Now that's the end of my introduction. I encourage you to ask questions as we go along. And indeed, if I've already raised mysteries or confusions, this would be a good time before I start to work on this. Okay, here's our basic setting. We're going to look at a correspondence. And I'll invite you to think of this as a supply correspondence. And so it's going to map from this set P, you can think of that as prices, into this set Q, you can think of this as an allocation. And I will use those words throughout, even though the interpretation of this correspondence will vary from time to time. Our basic requirements on these spaces is that P be a lattice and Q be a partially ordered set, but to some extent that's gratuitous generality. You can think of both of these as the Euclidean spaces that we know and love, and you won't miss anything as we go along. And this is the notion of unified gross substitutes that is going to be at the base of everything we do. It is that these two conditions be satisfied, and we could try to work through those two conditions, but before doing that, let's look at a picture. And so in this picture, of course, P and Q are going to be not only Euclidean spaces, but they're going to be two dimensions so that I can draw the picture reasonably. And so we start by saying, let's suppose we have two price vectors, P and P prime, and they map into two quantity vectors that I'll call Q and Q prime. And then we ask, what about the price that sits right there, which is the component-wise maximum of these two price vectors that I've looked at? And what about the price that sits right there, the component-wise minimum of these two price vectors? So I want to know what I can say about what I'll call P upper and P lower. So there they are, these two new price vectors that I'm interested in. They have to map into something. Now this is a correspondence. So P may map into not only Q, but lots of other things. P prime may map into not only Q prime, but lots of other things as well. But that's okay. My specification requires that for P and Q, I'd be able to pick up any Q in the image of P and any Q prime in the image of P prime. And then for this price, this P upper, the requirement is that it has to map into something that lies underneath those two bounds. So I can put that on a picture as well. So remember, P maps to there, Q maps to there. P upper may map to lots and lots of things, but at least one of them has to lie below the component-wise maximum of the two quantity vectors. And for P lower, the opposite is the case. At least one of the things to which it maps is going to be here, must be above the component-wise minimum of these two vectors. And so I go back to my definition. That's essentially what these two properties say. This is the element that I am required to find in the image of the max of the two price vectors, and these two inequalities together are the statement that it lies below those two bounds I identified. And this is the allocation that I'm required to be able to find in the image of the minimum of the two price vectors, and this pair of inequalities is the statement that it has to lie above the lower bound that I estimated. And so if that property holds for any pair of prices, for any pair of allocations that I choose in their images, then I say that I have this property of unified gross substitutes. All right, that's the property we're interested in. Some examples to suggest that this isn't a completely crazy thing. If I look at the supply correspondence of a competitive firm, and so its profit expression is the vector price times the vector of quantity, because I allow this to be a many product competitive firm, minus a cost function. That supply correspondence, given that the cost function has the usual properties that we want, given that it's a convex cost function, that'll exhibit unified gross substitutes. If I look at this problem, you can think of this in two ways. One of them is you can think of this as a prediction problem. Q is a set of outcomes, and the P's are probabilities attached to those outcomes, and you're asked to predict which outcome is going to be drawn. And so your best prediction is to identify the outcome or the collection of outcomes that have the highest probability attached to them. That's what this correspondence defines. That would exhibit unified gross substitutes. This kind of correspondence also arises as the limit as you crank the rationality factor up as high as it can go of a logit choice problem. And in that case, Q is again a finite number of goods from which you're choosing one. The P's are the utilities attached to those goods. In the ordinary logit choice problem, then there's some error on top of that that makes you choose higher probability goods with higher utility goods with higher probability, but it's not perfect. Crank up the rationality, and in the limit you get a correspondence that looks like this. So if I look at a monopoly firm practicing third-degree price discrimination, so it sells this many goods in this many markets, and in each market it satisfies a revenue maximization problem, and then it has a joint cost function. Again, if that cost function is convex, and we have the usual decreasing marginal revenue property we want out of the demand functions, this is going to satisfy unified gross substitutes. And then one preview of what we might use it for, look at a competitive exchange economy. If each of the individual supply correspondences, excess supply correspondences, satisfies unified gross substitutes, so does the aggregate. And we're going to show before that this gives us a sort of familiar result that the set of equilibrium prices is a lattice. And that's the same sort of result that shows up when characterizing the set of stable matches in a matching problem. And that's going to be this is going to be a nice sort of result to have in several applications. So those are some examples to suggest that this notion of substitutes is not perhaps too crazy. A couple of quick comments on its properties. One, I just mentioned, it aggregates nicely. So if I have correspondences that satisfy it, so does any convex combination, or in fact, any weighted sum of those correspondences. So this allows me to go from people to markets when talking about, say, competitive equilibria. And I can get an existence result here if I have a correspondence E of P, and I want to know when is there a P star such that E of P star is equal to 0, or put anything on the right side that you want here. And then I get essentially a version of the intermediate value theorem, that if I have two extreme prices that put me on either side of this value that I'm seeking, and I have the usual nice properties that I want from correspondences, then I know there's a price somewhere that satisfies that condition. And so in one dimension, this would indeed be the intermediate value theorem. And in higher dimensions, those theorems are a little harder. And it's unified gross substitutes that gives us a version of that. Some comparisons for how this fits in the other notions. The substitute notion that we know best is typically called weak gross substitutes. And this is a property of supply functions. And it is essentially the property that was expressed by the two derivatives that I was talking about when I was giving my motivation for looking at this. Intuitively, it's the property that raising the prices of everything else reduces the quantity supplied of good Z as the supplier substitutes from good Z into the other, now higher price, more lucrative items. And so we get the same kind of, or we get exactly that property if the correspondence E that we're talking about is indeed a function. So for functions, we have exactly weak gross substitutes, and we have the appropriate generalization of that, we think, for correspondences, that if we hold the price of good Z constant and the prices of everything else increases, well, we can't exactly say the quantity supplied of good Z decreases because we have potentially set value images in our map here. But what we can say is that there is some allocation after the increase in the other prices in which the good Z has decreased, or there is some allocation in the initial prices in which the quantity of good Z is higher than the allocation after the prices have increased. And so we have to make a selection from the sets here, but we can get the same sort of monotonicity property. We discovered, after we were a fair about into this, a paper by Polterovich and Spivak some time ago, looking at the notion of substitutes for correspondences. They have a more general notion than ours, a very general notion, though it's in the same spirit. One of the difficulties they find is that their notion doesn't aggregate, and that was a real disappointment for them, because they wanted to talk about excess supply functions for competitive economies. And they then introduced some conditions on the domain of their correspondence, the image set, and the correspondence itself that suffice to ensure that their notion aggregates. And once they do that, their notion is just the same as ours. And then on they go. And perhaps the best known notion of substitutes for correspondence is Kelso and Crawford. And they, looking at a matching market between firms and workers, posit an ascending bid wage formation process and show that if their demand functions exhibit the counterpart of their gross substitutes notions, then this process converges to a competitive equilibrium. Our notion is a little stronger than theirs, so ours implies theirs, but the converse fails. And roughly the difference is this. I have repeated here the two conditions that give us our unified gross substitutes notion. And the point is that when we are looking for this allocation, the allocation in the image of the max of the prices, we require that the same allocation satisfy both parts of these conditions. And when we are looking at this allocation, the one in the component-wise minimum of the price vectors, we ask that the same allocation satisfy both of these conditions. Kelso and Crawford's definition could be reformulated to look very much like this, but they would allow these two allocations to be different, and they would allow these two allocations to be different. And so it's the fact that we require the same allocation in each place, something we allow ourselves to describe as unifying these two conditions, that gave us the name unified gross substitutes. And that's what makes our condition stronger than theirs. It's easy to find examples. Not clear how natural are these examples, but it's easy to find them that satisfy theirs, but not ours. Another good pause for questions if they have come up yet at this point. This gives us the basic introduction to the substitutes notion.
Larry?
Yeah.
I have a very small question. I don't, this definition is for Rn or for lattices and partially ordered set?
Lattices and
definition.
partially ordered sets.
So what is QZ? I seem to misunderstand something basically in this. What does it mean?
I see. Let me rephrase that. I should have been a little more careful. It is for subsets of Rn that are lattices or partially ordered sets. So I want to keep the dimension.
Thanks.
And we could be more, we don't have to have it be subsets of Rn's, but for today it is, so I can write it nicely like this. But here's the inverse result that we would like to have. We're going to look at our correspondence E. We're going to ask it that it define our substitutes notion. We're going to ask it that it satisfy another condition. For a long time, we were not sure what to make of this condition. We used to call it just property X. And now we've given it the name non-semi-negativity in an effort to make it sound like it's not very strong. And roughly, it means things can't go exactly backwards. We'll go through what it means in a minute. And the result is that if the correspondence E satisfies those two conditions, then it has an isotone inverse. So then its inverse images are increasing in the strong set order. Let's see, to give an idea of this, so I want to explain what inverse isotonicity is and what non-semi-negativity is in ways easier than just plowing through the equations. And so the easiest way to look at inverse isotonicity is, suppose I have two prices and I have two quantities, and the quantities are ranked. If the quantities aren't ranked, which they may not be, because in keeping with the Euclidean interpretation, we're comparing vectors here. I don't have anything to say about them, but if they are ranked, then my requirement is that the smaller one is also in the image of the component minimization of the prices, and the larger one is also in the image of the component wise max. So I should have a picture of this. Here's my two prices, P and P prime, and they map into these two allocations that are ranked. Q prime is larger than Q. And so my requirement in this case is that this Q prime must also be in the image of the component-wise max of the two functions. And this Q must also be in the image of the component-wise minimum of the two functions. And so if you do that in this case, the inverse image of the minimum, the inverse image of Q is now this set, and the inverse image of the Q prime is now this set. And those sets are indeed nicely ranked in the strong set order. In this case, that result is pretty close to trivial because I have just two dimensions to work with. And so in particular, there's no overlap between these two inverse images. In more dimensions or with a richer correspondence, these might take much less obvious shapes, but the import of the inverse isotonicity requirement is that this inverse map be an increasing map. That's the inverse isotonicity we're after. It remains for the moment to explain this non-semi-negativity result. And indeed, instead of explaining this, I'm going to suggest some sufficient conditions for it. And we had the sufficient conditions first before we identified what their essential property was. So here is one such sufficient condition. And once again, it looks initially like a gibberish of notation, and I'm going to respond by showing you a picture. So here's my basic illustration of unified gross substitutes. The price vector P maps to Q, the price vector P prime maps to Q prime. Unified gross substitutes then requires that this one map to some vector that was below this upper bound, that this one mapped to some vector that was above this lower bound. And the non-semi-negativity requirement is the requirement that I can draw a pair of parallel lines, that's this one and this one, through this allocation and through this allocation, with the property, this is above the two lines and this is below the two lines. The lines can have any slope that I can find to fit in there. And the slope of the lines can depend upon the P's and the Q's that I've chosen. So I have gotten a great deal of freedom in being able to do this. So the reason I say we think of this as a weak property, the reason I say that it tells us things can't go exactly backwards, is what it precludes is the possibility that this quantity associated with the minimum price is up here somewhere, and this quantity associated with the maximum price is down there somewhere. Then I can't get them separated appropriately. So that's one sufficient condition for that property that we need. If this is a constant sum correspondence, so if my allocations always sum to the same thing, it will satisfy the non-semi-negativity. And where do we see constant sum correspondences? Sometimes they appear naturally. The logit choice problem, or equivalently the prediction problem that I showed as an example that satisfied unified gross substitutes, those are constant sum source correspondences. Other times we create constant sum correspondences. So we create a new fictitious good called Q0 and a fictitious price called P0. Almost always this price turns out to be 1 when people do this. And a collection of weights here, these often also turn out to all be 1s. And we require that this fictitious quantity satisfy this property. And now we get an expanded correspondence, and we ask that that expanded correspondence satisfy unified gross substitutes. This is the sort of thing that Berry, Gandy, and Hale do. So they apply their substitute notions to this expanded correspondence, which we've just automatically converted into a constant sum correspondence. And so this is a pretty common kind of thing to do. That will satisfy the non-semi-negativity property. Competitive profit maximization, that satisfies this non-semi-negative property. So we don't regard that one as too important a requirement. A few connections. In many circumstances, this inverse correspondence that we're talking about will itself solve a maximization problem. I mean, you can always find some maximization problem. You can always invent one that it solves, but sometimes it solves a quite natural one. Sometimes there's a nice dual argument that gives you that. And then we can use the usual monotone comparative static results from Topkis and from Milgram and Shannon to tell us when this inverse is isotone. And we can show by examples that those conditions don't imply unified gross substitutes. They aren't implied by unified gross substitutes. So we have a non-nested relation with them. Let's skip this. There's this notion of P functions for linear functions that was generalized to nonlinear functions and that essentially delivers our non-semi-negativity. Since I claimed that was not important, we'll skip that. I said Berry, Gandy, and Hale were the immediate motivation for this. They were talking about demand functions. And they were interested, they showed that their conventional weak growth substitutes and connected strict substitutes gives an inverse that's not only isotone, but is point valued. And they really liked the point value because they thought that was a nice input to lots of sort of estimation problems that they would want to be doing. We get that a demand function has an inverse isotone. We get that with unified growth substitutes, which for functions is identical to weak growth substitutes. So we don't get the point valuedness when we drop this assumption. So for functions, we have a weaker set of assumptions than they do, a weaker set of conclusions. For correspondences, we have the generalization of weak growth substitutes and we get the generalization of isotone. We could add an additional assumption and get the point valuedness if we wanted to. And that additional assumption is very much like their connected strict substitutes. And so then we get a generalization of their result to correspondences. That was our immediate sort of narrow motivation for this. All right, that's the end of inverse isotonicity and properties and connections. And so now I'm going to move on to put this to work. Once again, a good time for questions if they've come up. All right, time to make this look a little bit more like a game. And so I'm going to introduce what I'm going to call the equilibrium flow problem. And the building blocks are going to look like this. There's going to be a set of nodes. If you want, think of these nodes as people or traders. There's going to be a set of arcs between nodes. In some case, we might have these nodes completely connected. There may be an arc between every pair of nodes. We might think of an exchange economy like that. In other cases, we might have the nodes divided into two groups, say male and female, and there might be arcs only between males and females, but not within the males and not within the females. That would give us something that looks more like a matching problem. In another case, some subset of these arcs might be viewed as sources and another subset as destinations. And the arcs might trace paths from the sources through the destinations, through some intermediate nodes. That would give us what looks like a routing problem. So this set of arcs can take lots of different shapes that will allow us different interpretations of this problem. Each node is going to be endowed, I call it a flow here, but think of this as a quantity that's sitting on that node. Sometimes that quantity will be positive, sometimes that quantity will be negative. One interpretation of the equilibrium flow problem is going to be as an optimal transport problem. And in the original version of the optimal transport problem, Monge's original formulation of this problem, there were a collection of piles of dirt and there were a collection of holes. And your task was to get the dirt into the holes in a cost minimizing way. So in this case, if we wanted to capture that, we'd have a collection of nodes with negative values of Q. That's the dirt, and the negative value tells you you have to get that away from that node. And we'd have a collection of nodes with positive values. Those are the holes. And positive values would tell you you have to get dirt into those. We're going to describe flows along these arcs. Those are going to be given by mu. And we're going to attach prices to the nodes. And then for each pair of nodes, X and Y, we're going to describe what I'll call a rent function, R of X, Y. I'm going to write the rent function as a function of the price vector, but it's going to depend only on PX and on PY. X is the source node on this arc. Y is the destination node of this arc. And we're going to ask that the rent be increasing in Y and decreasing in X. And so an easy interpretation of this, if you want, is you're a trader and you're carrying something from X to Y. This is what you have to pay for it at X. This is what you get for it at Y. And the difference is the rent you earn by moving something along that arc. That's my equilibrium flow problem. And now in the equilibrium flow problem, I'm going to want to have an equilibrium flow, and that's going to require the following. This is a feasibility condition. This tells you that these flows that you have created take all of the dirt away from the nodes that have negative values on them and get all of the dirt that's needed at the nodes that have positive values on them. And so since I haven't actually defined that first symbol there, we have to live with the interpretation of this, but this will tell us for any node that has a negative value of Q on it, the net sum of the flows out of that node equal the absolute value of Q. And for any node that has a positive value of Q on it, the net sum of the flows into that node equals Q. So that's our material balance condition. This one tells us we don't earn any positive rents in equilibrium. So all of the flows go along non-positive rent arcs. This is going to be a condition on the prices that we can set. And this one tells us we only move flow along zero rent arc. And so the interpretation of these last two rent conditions is that if we had an arc with a negative rent, no one would want to carry goods along that arc. And so we can't do that. If we had an arc with positive rents, people would want to carry an unlimited amount of goods along that arc. And so we can't do that. And so in the end, there have to be no positive rent arcs and flows moving only on zero rent arcs. It's worth noting that this rent function, we do not require to be linear in the prices. A very common form of this is to make the rent function something like Py minus Px minus some cost that is specific to XY. And that's a fine example, but we don't require that. Now, why would we be interested in the equilibrium flow problem? Because depending on how you specify and interpret the nodes in the arcs and the flows in the prices, we have, as special cases of this, matching problems, including matching problems with allowing some agents to be unmatched. And this connects to an idea that I raised earlier. If you have a matching problem, you typically first divide into two groups, say men and women. You assume that arcs flow from men to women, maybe not from every man to every woman, but only from men to women or women to men, but not within group. And if you do just that, your equilibrium flow will force everyone to be matched. Sometimes that may be appropriate, sometimes not. If you want unmatched agents, what you do is introduce a new fictitious node, call it Q0, and you interpret being matched with Q0 as being unmatched, or you interpret a flow from one of the men to Q0 as an indication that man is unmatched, a flow from a woman to Q0 as an interpretation that woman is unmatched. And this is just the sort of fictitious node that I introduced earlier as a device for making sure we satisfy the non-semi-negativity. And so this using this fictitious node to pick up that condition is a very natural thing to do in many applications of the equilibrium flow problem. We can talk about assignment problems. Now we're not matching men to women, but people to houses or something like that. We can talk about hedonic pricing. In this case, on one side of the market, we have houses is the usual example of hedonic pricing. On the other side, we have people who are purchasing houses. And in the middle, we have nodes that identify the characteristic of those houses that are priced in the hedonic pricing application. Optimal transport is an obvious example. We can represent dynamic programming problems in this way, and we can represent various versions of routing problems as equilibrium flow problems. Again, many of these applications are familiar. There's a tremendous literature on optimal transport, almost entirely within the quasi-linear case, the case where these rent functions are linear in Px and Py, and that's something we're not going to require. Okay with the equilibrium flow problem, or questions about the setup? Now I will tell you some results that we have for this. One thing we can do is ask, if we fix a price, what does the set of exit flows look like such that there exists an equilibrium flow giving us those prices and those quantities? If this were a matching problem, for example, fixing the prices is a lot like fixing the preferences in the matching program. And then fixing the exit flows is a lot like asking who's going to be matched and who's going to be unmatched. And then identifying the equilibrium flow is identifying the stable match. And so one of the things we get is that this correspondence then, well, it satisfies unified gross substitutes. We get that property fairly easily. And that in turn tells us that this correspondence is inverse isotone. We can apply our inverse isotonicity condition for us. As I indicated earlier, we have a constant sum correspondence here. And so automatically we pick up the non-semi-negativity condition. And that tells us then that for any, that should be a P, for any P, this inverse is a lattice. And so this is the familiar set of stable matches is a lattice result that we know from matching theory. First I saw this was Demange and Gale a long time ago. And typically we have this result for the bipartite case. And now we have this for we have this for more general versions of the matching function. This property that this correspondence exists and satisfies unified gross substitutes holds for the bipartite case, holds for all sorts of other specifications of the arc matrix. And so we get a more general form of the lattice result. We can ask about the existence of equilibrium. When does there exist an equilibrium flow? So this time I'm going to ask, given that we've attached the quantities to the nodes, we've arranged the piles of dirt in the optimal transport problem, or we've identified who has to be matched in the matching problem, we've identified the characteristic of the houses and the consumers in the hedonic pricing problem, when can we find prices and flows such that we have an equilibrium flow? So we're going to give an existence result for equilibrium flows. It's going to require two sorts of conditions. First, I'm going to take these in opposite order that they're written. When I look at the specification of the rent function. This is the specification of the preferences in the problem. This has to satisfy a no profitable cycles condition. In many network problems, this is or many allocation problems, this is a no cycles condition. So there are a lot of implementation theorems that have a no cycles condition. In the case in which this is a linear function, so when R looks like something like Py minus Px minus some cost that depends on the link xy, this no profitable cycles condition is a statement about the value of these costs. It's a little bit more involved in that when you drop the linearity here, but the spirit is the same thing. I must not be able to find a sequence of nodes that I can put together in a cyclic directed path with a property I can earn positive rents by running around that cycle. Because if I have such a condition, I'm never going to find an equilibrium flow, because I'm never going to be able to find prices that will satisfy the non-positive rent condition. Intuitively, when I ask my agents in this problem what they would like to do, they're going to want to run around this cycle forever and ever. So I need that. That's to make sure I can find prices. I have to be able to find two things. I have to be able to find a price and a flow. So I have the condition that's going to allow me to find a price. I have to be able to even find a feasible flow. It might be, if we think of the transport version of this, of getting the dirt into the holes, if there aren't enough links in my system, I might not even be able to do that. And so I need a feasibility condition there that's going to look like this. I'm going to look at any sort of subset of nodes called B. So there's my collection of nodes that I call set B. I draw this circle around them. And I'm going to say that's a retaining set if I have arcs coming into B, possibly from other nodes in the network. I have arcs within B, but I do not have any arcs that start in B and point outside. And now my basic feasibility condition is going to be that for every retaining set, Q of B has to be non-negative. Now, what is Q of B? This is the sum of all of the quantities sitting on those nodes. A positive quantity means you want to bring things into that node. And so a retaining set is one that I can bring things into, but I cannot take things out of because there are no links going outside. I can rearrange things inside. I can bring things in. I can't take things out. And so if I'm going to have any hope of getting my flows to balance, it better be that on net, I want to bring things into this retaining set, not take them out. It's obvious that that's a necessary condition. If I ever had a retaining set and my allocation was sense that I needed to get things out of that retaining set, I would be dead from the start because there's no way to get them out. That's what it means to be a retaining set. The interesting thing, the thing that requires the work here, is that that's a sufficient condition as well. As long as every retaining set has that property, I can always find a flow that gets things from where they want to go to where they want to go. And as long as I have the no profitable cycles, I can find prices that make sure that that flow is only using zero rent arcs, and all the other arcs have negative rents. Hall's marriage theorem is a special case of this condition for the bipartite matching problem. And so this is, think of this as generalization of Hall's theorem. The ideas used to prove this are roughly the same as the ideas that appear in Hoffman's circulation theorem. So we can't claim a whole lot of insight. The way we prove this theorem is we take any general equilibrium flow problem and we associate it with it a reduced problem that's a bipartite problem. And roughly we do this by, in our original problem, looking at the time, let's not talk about how roughly we do this. We reduce the original problem to a bipartite problem. We use familiar results, mostly Hall's theorem, for getting an existence in the bipartite problem. We show that we can extend or that solution to the bipartite problem to a solution to the entire problem, as long as we have the no profitable cycles condition and as long as we have that feasibility condition. I would talk about another set of correspondences that I would say have the polyhedral growth substitutes property, and that's because because these results are built on submodular polyhedrons. This is mostly useful because you get to say lots of, or talk about lots of nice things that I didn't know about until I did this. We skip all that. And so what have we gotten out of this? The equilibrium flow problem, as I said, contains a lot of familiar problems, maybe some new ones, but a lot of familiar problems as special cases. The key result there, the inverse isotonicity result, allows us to either extend the results for these special cases, typically beyond quasilinear, where many of them have been pursued, or to make some new results. Many of the results we get are about the existence and the lattice structure of equilibria. For example, there's a literature on hedonic pricing. The standard result there by Chiapuri, McCann, and Nesheim is that you can reduce the hedonic pricing problem to a bipartite matching problem, and then you can reduce that to an optimal transport problem, and now you have wonderful results to optimal transport that you bring to bear, and then you work back to the original hedonic pricing problem. And that works nicely. To do this, you need to stick to the quasi-linear case because that's where the results for optimal transport are. We can generalize that. Gould and Sticchetti have a wonderful series of paper talking about competitive equilibria with indivisible goods. They have results about characterizations of substitutes in terms of single improvement or no complements. They have results about lattice structure. And we can extend that now to the case where we don't have indivisible goods already. Indivisible goods have properties that they use quite heavily in getting their results, and so we can get those for general competitive equilibria. We have other sorts of things we can do, but looking at the clock, it's time for me to say thank you.
Thank you very much, Larry. This was a very interesting talk. Any questions? Okay, so if there are still questions, so please send an email to Larry. He's at home in Yale, so doesn't run to anywhere. So
I'm happy to linger online for a few minutes if people want to ask questions less formally.
Yeah. So again, thank you very much, and see you all again in 2 weeks.
Thank you for having me.
Thank you.
Thank you.